Good morning.
Good
Good
morning.
morning, teacher.
All right. Let's start chapter 4, which is about the sound waves. The first section, we will define what sound is. In second section, we will talk about the intensity of the sound. And in the third section, we will talk about the harmonics, which is the instruments, how some instruments produces the sound. We will talk about them. Now, the first one is what is the sound and how sound is produced. The first section is talking about this, and we know that sound is a wave, and sound because all waves are produced by a vibrating object. Sound is also produced by a vibrating object. So this vibrating object can be a loudspeaker. So the cone of the loudspeaker, as you see, it's vibrating. It can make a sound. Or it can be a vocal cord while you are talking, so it can make a sound. Or it can be a tuning fork, and then which is a device which in an experiment. Tuning forks prongs can vibrate and then produce the sound. So if tuning fork's prong is vibrating, so it's swinging right left, and then when it's swinging in one direction, it forces the air molecules to come closer. And these air molecules, when they comes closer, produces a region of higher pressure and density than normal atmospheric pressure. So remember, when you compress the molecules closer, that region is called compression. But this tuning fork, when it's moving one direction, if it produces here a compression, when it moves or vibrates in opposite direction back, so when it's swinging back, it produces a region which is low pressure. So air molecules spread apart, and then when the air molecules are spread apart, we produce a region of lower pressure or lower density than the normal, which is known as rarefaction. So then we can say that vibrating objects produce the sound. This vibrating object sets air particles into vibration with the same frequency, and of course in the air it produces regions of high pressure, which is called compression, and regions of low pressure and density, which is known as rarefaction. And uh, when the tuning fork vibrates with simple harmonic motion, so the air molecules also vibrate back and forth with simple harmonic motion. So tuning fork is doing that. It is the simplest device which produces the sound. So because prongs are vibrating with simple harmonic motion, because these prongs are setting the air molecules into vibration, air molecules are also vibrating with simple harmonic motion, and then produces regions of low pressure, high pressure, low pressure, high pressure, low pressure, high pressure, and so on. And as a longitudinal wave uh, travels or along a longitudinal wave, as you see, pressure and density of air changes as a sine curve while sound wave travels through it. So then high, low, high, low, high, low. It's like this. If I draw a pressure or density graph along this longitudinal wave, so high pressure corresponds to crest, remember. Lowest pressure corresponds to trough, which is rarefaction. Highest pressure corresponds to crest again, and then trough again. And between crest and trough, there is the normal atmospheric pressure, which is the equilibrium position. So the crest of the sine curve corresponds to compression, which is region of higher pressure. The troughs of this sine graph corresponds to the rarefactions, which is the regions of lower pressure, lower pressure, lower pressure, or lowest pressure. And uh, but every vibrating object can produce this sound. However, a human ear cannot able to hear every sound. So we can hear a sound of frequency between some specific values. So which is we say audibility. Audibility of a sound depends on frequency of the sound, frequency of sound produced by the source. And human ear can hear a sound whose frequency is greater than 20 hertz and less than 20,000 hertz. We hear this region, this interval, this range. But if frequency is of a sound is less than 20 hertz, so this sound is called infrasonic sounds. We cannot hear that, but some animals can hear these infrasonic sounds. And, elephants, for example, they uses these infrasonic sounds to communicate. But some sounds which is greater than 20,000 hertz, they are called ultrasonic sound waves. And again, some animals can hear this sound, which is the dogs and bats can hear ultrasonic sound waves. But human audible range, audible sound will be between infrasonic and ultrasonic. So which is audible region between 20 hertz and 20,000 hertz. Some marine animals, such as dolphins, use ultrasound waves to locate distant objects. So they can understand, they send the sound waves into the sea, and then these sound waves reflects back from a fish in front of dolphin, and this dolphin can get this reflected sound, and by this sound this dolphin gets information how far this fish is, how big is this fish is, or is it moving away or approaching, like a radar. It's just the same method. So a dolphin produces short sound pulses, which is short sound pulses mean ultrasound, short wavelength sound pulses that travels through the water, and bones of distance objects, bones of means reflects back to the dolphin. From these echoes, this reflection, dolphin can determine the size, shape, speed, and distance of their potential prey, and then just as a radar which some policeman uses to detect the speed of some car on the road. And one echolocation is this phenomenon is known as echolocation, but human also able to use echolocation in medical science. As I said, in traffic control they use the radar. Radar is also a kind of echolocation. And another one is using ultrasound image, ultrasound waves to get the image inside the human body. And ultrasonic waves can be used to produce image of objects inside human body. A typical frequency used in ultrasonic device is about 10 megahertz, which means 10 times 10 to the power of 6 hertz, yani 10 to the power of 7 hertz. It's so big frequency. So the images produced by ultrasonic waves are clearer and more detailed than those that could be produced by lower frequency, and of course lower frequency means longer wavelengths sound waves, because short wavelengths of ultrasonic waves are easily reflected of small objects, but longer wavelengths like audible waves or infrasonic sound waves, they pass around small objects, so they cannot produce a sound picture because they pass around, they don't reflect. That's why physicians commonly use ultrasonic waves to observe fetuses. So the reflected ultrasonic waves from the fetus are converted to electric signal, and which forms an image on a fluorescent screen like this. So then this image allows doctors to detect some types of fetal abnormalities. Ultrasonic waves is maybe the first imaging technique. It is simplest, but not dangerous. It's not dangerous for human body, but it's just a first way. Not, of course, later some other techniques are they provided, like X-rays or MRIs. This is, of course, primitive compared to X-rays and MRIs, but this is safer than these two other techniques used in medical science. And this was the ministry exam question. So, which of the following is used in medical science to detect the object inside the body, which is ultrasound waves? Ultrasound waves. And next is we will continue defining the wave, which speed of a sound wave. Because it's a wave, speed of the sound wave also uh, depends on the medium. So basically, speed of a sound wave depends how quickly one particle can transfer its vibration to another particle. So if molecules are close, like solids, than the liquids, or liquids molecules are closer than the gas molecules. For that reason, sound is fastest in the solids than liquids, or sound in the liquid is faster than the gases. Because molecules of solids are closer than molecules of both liquid and gases, solids responds to the disturbance more rapidly. That's why sound is fastest through the solids. Like here, there's a table, you see that gases, liquids, and solids. In gases, for example, air, sound is traveling at a speed 346 meters per second, but in water, it is almost 1,500. In solids, like aluminum, like copper, like iron, 3,000, 5,000 meters per second, about this. As you see in solids, much, much faster than the gases. And another thing was temperature, which changes the property of the medium. If you change property of a medium, so you can also change the speed of a wave, so sound. Speed of sound in gases changes with temperature. So as temperature rises, as you see here, air at 0 degrees Celsius, air at 25 degrees Celsius, air at 100 degrees Celsius. So there is slight difference between these numbers. At 0 degrees Celsius, 331. 25, day temperature 346, but at 100 degrees Celsius 366. As you see, as temperature increases in air temperature increases, the speed of the sound, speed of the wave traveling in the air also increases. So as temperature rises, the amplitude of the vibration increases. So every particle's molecules are vibrating, but while they are vibrating, as temperature increases, they start vibrating with a longer amplitude. So then the particles of the gas collide more frequently if temperature increases. So disturbance can spread faster in gases at higher temperature. The difference in speed due to the temperature change is not as noticeable as this liquid in the solids. Solid and liquid particles are almost very close to each other. So increasing the temperature does not make a big effect in the speed of the sound in the solids or liquids. This was the ministry exam question of 2017. They asked, in which of the following substances the temperature variation of the sound is more noticeable: solids, liquids, or gases? So in gases it is more noticeable, so in solids and liquids less noticeable if temperature changes, the change in speed of sound. And sound propagates, waves propagate. Propagate means travels, travels in all directions, which means into dimensions, X, Y, Z. So that's why when the sound waves are traveling, so we can see that it's moving on a spherical shell. So sound waves are approximately spherical. When, for example, now I am talking, that sound is traveling in all directions, just making some spheres. And these spheres are represented with series of circles surrounding the sources. Normally they are spheres, but we are not able to draw the spheres on a piece of paper. That's why instead we are going to draw circles for these spheres. And this is the sound source, which is a loudspeaker. As you see around the speaker, there are some spherical spheres which represents the compression. These circles or these spheres are representing compressions, which is high pressure region, high density region. And it is also trough of a sine wave, and its name is now called the wave front. This is another sphere, another compression, another high pressure and high density region, or another wave front. This is a third compression, a third high pressure, high density region, a third wave front, a third crest for the sine wave. It's written trough, but it's the crest. Yeah, still I didn't change this in the lesson. It was written also crest. This is not crest, it is going to be trough. These wave fronts are the regions of high pressure and high density, which is known as crest of this sine wave. But between two wave fronts, between two compressions, there is rarefaction, which is the region of low pressure, low density, which is known as trough of this sound wave. Okay, if we draw the pressure graph, pressure wave or density wave, we see that yes, every wave front corresponds to a crest. Another wave front corresponds to another crest. Third wave form corresponds to third crest. But the refraction, which is the trough, corresponds to trough of this pressure graph, another trough of this pressure graph, and so on. And separation between two compressions or two wave fronts is called one wavelength. So from here to there, it is one wavelength. From here to there, it is another wavelength. And these lines, directional lines, which is called rays, indicates the direction of the wave motion. They are called rays. This red line, another red line, another one, one more you can draw here, one more you can draw here. So you can draw many rays, which indicates direction of wave motion. They are radial lines, which means lines on the radius. They are radial lines perpendicular to wavefront. Yes, they are perpendicular to wavefront. These points are perpendicular to wavefronts, and they indicate direction of wave motion or direction of the sound. And uh, wavefronts of a small portion of a spherical wave that is many wavelengths away from a source are nearly parallel planes or parallel plane waves. So what does it mean? This is a spherical wave. This is another spherical wave. As time passes, these waves are approaching from the source, moving away from the source, and then another and another. So as wavefronts are getting away from the source, so a part of them is getting closer a straight line, a plane wave for that as it's called. When it is very close, it is not close to straight line, as it's a curve. But when the distance is 2 lambda, it is getting closer to a straight line. When it is 3 lambda, much closer. When the distance is 4 lambda, almost a straight line, which means as a wave is moving away from the source, many wavelengths away from the source, so a part of this wave can be thought as a plane wave, which is straight line. So as wavefront moves away from the source, a small portion of this spherical wave, this is a small portion, can be traded as a plane wave. This is just an information, but don't forget this can be this spherical waves, a portion of this spherical wave can be treated as a plane wave when, if this wavefront is many wavelengths away from the source, not very close, it must be very wavelengths away from the source. So in this case, you can treat a portion of this wave as a plane wave. And next, we will define a break in the sound barrier. What does it mean? So first, we know that as sound is traveling, it produces, as sound is produced, wave fronts are produced, and then they all travel on circles. So this is an airplane which is running but not moving. So as you see, sound is produced and then propagates in all directions on these circles. And separation between the wavefronts are the same in all directions. So wavelength is the same in all directions. But if this airplane starts moving to the right, as you see here, it's moving to the right. In this case, the separation between the wavefronts in front of the airplane is getting closer, which means wavelength of the sound waves in front of the airplane is getting closer, getting shorter. But wavelength of the sound waves behind the airplane is getting longer. So, but if this airplane is moving with speed of sound, so these wavefronts in front of the airplane meets each other. These lines meet each other, and they, right here, they start to adding each other, because you know that's this every crest, every wavefront corresponds to a crest. If all these crests meet each other in front of the airplane, so they will produce a wave with a longer, very long amplitude. If amplitude is longer, which means power, amplitude, square of the amplitude determines the power and energy of a wave. So for that reason, in front of the airplane forms a region of very high pressure and high density sound. So when airplane attains the speed of the sound, the disturbance accumulate in front of the plane right here, accumulates and increases the amplitude of the resultant wave. And this resultant wave produces a sound wave which is a great power, which is a great energy, which means it is very loud sound. So that loud sound is known as shock wave. So accumulation of the sound waves in front of the airplane produces shock waves, but just in front, just in the, at the tip of the airplane. But if airplane exceeds the speed of the sound, if it so moves as a speed which is greater than speed of sound, like this one, in this case, these shock waves also accumulate, but not at the tip, at the edge. You see here, here. These waves are accumulating, and here along the edge, these waves are accumulating. When speed of the plane exceeds the speed of the sound, shock waves will form at the edge of the airplane right here. And superpose. Superpose means interfere. When they interfere, they will increase the amplitude and then will give a great power, very big noise. So superpose to give a huge explosion. This is named as breaking the sound barrier. Breaking sound barrier by an airplane gives rise a huge amount of energy. And this sound is heard just as a very big boom, like in these movies. Let's watch them right here. Maybe you cannot hear the sound because I didn't. Okay, we cannot hear the sound. I will skip it. Anyway, so when the airplanes are moving at a speed equal to the speed of sound or greater, so sound waves accumulate So in at the tip or at the edge of the airplane, these accumulated sound waves are called shock waves. And this case is called breaking the sound barrier. When the airplane speed is greater, this was the ministry exam question. What does breaking sound barrier means? If an airplane speed is greater than speed of sound, so then shock wave forms at the edge of the airplane, and this event or this phenomenon is known as breaking the sound barrier. And there are two conceptual challenge questions, so you can read it later. So we will continue the sound waves. Yes, and a source produces a sound. It's an ambulance, for example. The frequency of the sound wave only depends on the sound source. What is how many times vibration this source makes? So you hear the frequency of the sound at the same frequency. You will hear the sound with the same frequency. But an observer, when observer is listening a sound, we say that this observer hears a pitch. The frequency observed by the perceived by this observer is called pitch. So this sound, this source is making a sound with some frequency. This observer is perceiving the sound with some frequency. That perceived frequency is called pitch. The frequency perceived by a listener is called pitch, and this pitch depends on some factors. There are four factors which is talked in your book. One of them is loudness. When sound is louder, human can uh, think that sound frequency is a little higher, or the pitch is higher. In fact, it is not, but human eye is not so perfect. So you can hear a louder sound at a different pitch than a soft sound. So background noise. If there is a music playing, if nobody's talking, you hear that music at a different tone. But if somebody's talking, there's a noisy environment, the same music is playing. So human ear can uh, detect that sound at a little different. So for that reason, this background noise also affects the pitch observed by the human ear. Third one is frequency of the sound source, of course. If sound source frequency is changing, so pitch observed by the listener must change. And the fourth one is the more important one, because we will talk about this, the relative motion between the sound source and the listener. So if this sound source and listener are relatively approaching each other or moving away from each other, so then this listener can hear that sound at a different pitch. So this is called Doppler effect. Now we are going to study this. So how high or low we perceive the sound to be known as pitch. By the time how high or how low we perceive a sound doesn't mean that volume in physics. It's about the frequency. It is about the pitch. Pitch is subjective to the listener. Subjective to the listener. Yani source produces a sound with frequency, but listener hears a sound with some pitch. So that sound, this frequency is called pitch. So pitch is subjective to the listener, while frequency of the sound wave is an objective quantity that can be measured. So it belongs to the source. And when there is a relative motion between the sound source and an observer, a change in frequency is observed. A change is observed in the frequency perceived by the listener from the original frequency. This frequency shift is known as Doppler effect. Like as a car is approaching to you, horning, you hear a different pitch. When it is moving away from you, you hear a different frequency, different pitch. So this relative motion, when it's approaching and moving away, this frequency shift is known as Doppler effect. So relative motion between the source and listener results in a change in the pitch, which is the definition of Doppler effect. And if a sound source and a listener are relatively approaching, like this one, an ambulance is approaching to a listener. So because wavefronts are getting closer, wavelength decreases. And this listener perceives a sound which is shorter wavelength. Which is shorter wavelength means higher frequency or higher pitch. So then if a source is approaching to you, you are going to hear a higher pitch than the original frequency. So because wavelengths get closer, wavelength decreases, but frequency of the pitch increases. If a sound source and the listener are relatively moving away, like this ambulance is moving away, the listener or observer perceives a lower, smaller frequency, which is known as lower pitch. Why? Because behind of the ambulance, the wavelengths are longer, so the wavefronts are farther. Wavelength becomes longer according to this observer, and for that reason, frequency becomes smaller, so in the lower pitch. Wavelengths get farther, and then wavelength increase. As wavelength increases, frequency of the pitch for this observer decreases. And that's why this observer will hear a lower pitch when this ambulance is moving away. So basically, we can say that if a listener and an a source approaches each other, so pitch rises. So this observer, listener, hears a higher pitch. When source and listener are relatively move away each other, so in this case, pitch drops and you hear a lower pitch. And the equation for calculating the perceived frequency or the pitch frequency, which is f prime is the pitch frequency, this equation is used, which is equal to f, which is original frequency of the source, multiplied by v plus minus vo. V is the speed of sound in air, both in numerator and denominator. Plus minus vo, vo belongs to the observer. V plus minus vs, which belongs to the source. For example, let's show. A police car moves at a speed of 90 kilometers per hour. So this is and emits a siren of frequency 1000 hertz. This 1000 is f, which is original frequency. And police car is making this sound, which is the source. And this source is traveling with 90 kilometers per hour. So this 90 kilometers per hour must be converted to meter per second. By dividing 3.6, you can do that. And it is the speed of the source, Vs. So this 90 kilometers per hour is Vs. And what is the frequency of the sound as detected? Detected frequency means pitch. So f prime is the question. By a standing observer. If the standing observer is standing, so its speed is going to be written here 0. Pardon. So police car is this source, this is observer, sorry. This is police car is the source, it's going to be written here, and the observer is the standing, because standing observers is the OVO, VO must be written here 0. And speed of sound in air is given 340, so you are going to write here 340 and 340. Only different thing you should determine is positive, negative, or positive and negative. Numerator, you don't care because VO is 0, but in denominator, now be careful. So when they are approaching each other, so f prime must be greater than f. F prime must be greater than f. To make f prime greater, you should make denominator smaller. To make denominator smaller, so you should subtract them. That's why your equation for this question will be v minus v source, or v minus vs. So denominator will be smaller. Smaller denominator will let f prime to be greater. Such a logic can be used to solve these problems. There are other problems here, then all are going to be used with the same method. And this is the...
Can you repeat, please?
Which one?
You said it must, f prime must be bigger than f.
Yes,
I didn't understand.
Yes, because approaching, if a source and an observer is approaching each other, which means pitch must increase, relatively approaching. F prime must increase. It will be greater than 1000. This is 1000, is it? The original frequency. So
Yes.
in this case, f prime must be greater than 1000 when they're approaching each other, or will be less if they are moving away from each other. But now they're approaching. Question says approaching. They are each other.
Okay.
And that's why I should write this equation in the form that f prime will be greater than f. How? So how can I make this increase? By making denominator here decreasing. How can I make this denominator less? By adding or by subtracting? So you should subtract, of course. If you
Yes.
subtract Vs from V, so which means you can make f prime greater than f. That's why your equation will be written as like this. F prime is equal to f multiplied by V divided by V minus Vs and brackets.
But if it's moving away, we have
Yeah,
to
moving away
decrease it.
is positive. If they are moving away, if the source is moving
Ah,
away,
okay.
source is moving away, this time f prime will be less than f. That's why you should make denominator positive to get to calculate the f prime correctly.
Okay, thank you,
And in
teacher.
take your malzeme, in the lesson we explained it. Just everything is written there. There, why should we do that? But just first determine f prime will be greater or smaller than f. If greater than f, so this must be negative. If less than f, this must be positive.
Okay, teacher, I get it.
Okay, and then this is the end of the first. Let me explain by the time. This is moving away part. Okay. Then after that, we have 3 minutes in this lesson. Then we will continue with section 2. A parked ambulance emits. Now this time the ambulance, which is source, is parked. Ambulance emits a sound of frequency 1200 hertz. What frequency is detected by an observer moving with a velocity of 20 meters per second? A, towards the ambulance. B, away from the ambulance. So then if this observer is moving towards the ambulance, so every sound source, as I said, has a certain power. For example, you have a loudspeaker at home. One loudspeaker is 10 watts. It's its power. Another loudspeaker, identical loudspeaker, also 10 watts. But if you use both of them together at the same time, total power becomes 10 plus 10, which is 20. If you put a third speaker, so it becomes 30. So then when you increase the number of speakers, of course, power of the sound will increase. And power is defined as the rate at which energy is transferred. So the rate of energy transfer is known as power. This is the definition of the power. So if we divide energy spread by the source and by time, energy divided by time, we calculate the power of that device. So unit of power is watt. As I said, every speaker also has power as watt. But some speakers can be more powerful than the other one. Like this. This is a small speaker, which is say that 5 watt. But this is a very big speaker, which is say 50 watt. Of course, if they are at the same distance, if two listeners are at the same distance from these two loudspeakers, so the one on the left will hear a high intense sound, will hear louder, because power of this speaker is great than this one. So powerful speaker is heard louder than the less powerful speaker. The greater is the power of the sound source, the greater is the wave intensity of the sound here heard. Here heard powerful, or the more intense sound, here is less intense sound. So weaker speaker is heard softer. So the smaller the power of the sound source, the smaller is the wave intensity of the sound heard by listener. So wave intensity, which is represented by I, of a sound is directly proportional to the power of the sound source. As power increases, wave intensity at a point increases. Second thing is, if two listeners are at different distances from one source, so this distant listener is closer, that one is farther. So the one, which one will hear a softer sound? Of course, the one farther. So closer one hears the louder sound, but the farther one hears a softer sound. Listener closer to the sound source hears louder, closer to the sound hears it louder. Wave intensity is greater at a location closer to the source. So which means shorter distance, greater wave intensity. But listener farther from the sound source hears a softer sound, which means wave intensity is smaller at the location farther from the source. So longer distance, smaller wave intensity. Then I can say that yes, wave intensity is inversely proportional to the but square of the distance, not distance, square of the distance. R squared. If I say this distance is R, so sound intensity I is inversely proportional to square of the distance from the source. If we combine these two equations, which is this is proportionality, sound intensity is proportional to power of the source. Sound intensity is inversely proportional to square of the distance from the source. So sound intensity is proportional to power over R squared. And if we add here is a constant, we can write an equation. As distance from the sound source increases, wave intensity decreases because, now we will talk about the reason in terms of physics. This was in terms of our daily experiences, but this is about the physics. Why? As distance from the source increases, why wave intensity decreases? Because power emitted by the source P, so this source is emitting some power here, as it's expanding, it starts to distribute over a larger area. So when it is closer, at the distances R, this area is small. As distance increases, that area becomes larger. So much more increases, area becomes larger. Yani initially the area is small. As the sound is expanding, area over which the sound is distributed is increasing. As a result, wave intensity of the sound is decreasing. So as a result, wave intensity of the sound, yani energy per area, decreases as distance from the sound source. The equation for calculating the wave intensity is power divided by area. Wave intensity I is defined the rate at which energy of a plane wave flows through a unit area. So energy and power divided by area is the wave intensity. So its unit will have watt, power has a unit of watt, area has a unit of meter square, watt per meter squared. Sound wave is distributed over a spherical surface, we know that. If sound wave is distributed on a spherical surface, then area of a sphere is 4 pi r squared. I'm going to insert here area of a sphere, and we'll get the equation for calculating the sound intensity at a specific distance from the source. So I is equal to power divided by 4 pi r squared is the equation for calculating the sound intensity at a specific point at a distance of r from the source. There are some questions about them. It's not so difficult. You can use basic mathematics to get the intensity. So be careful only. So power is in watt, and the R must be in distance in meters. So you will get the sound intensity at a point from in watt per meter squared. And audibility of the sound, remember in section 1, we talked that it depends on the frequency. Human ear can hear some frequencies between 20 hertz and 20,000 hertz. But this is not the only factor which determines the audibility. Second factor is wave intensity. Wave intensity of the sound can also de determines the audibility. For that, as an audibility of a sound depends on two things. None of them is the frequency of the sound source. Second one is intensity of the sound at the location of the listener. So then we will talk about human ear can hear some intense sound but cannot hear some soft sound. A diagram is prepared for defining the audible sounds. Sounds of every different frequency has a minimum value of minimum wave intensity to be audible, known as threshold of hearing. This lowest blue curve is defining the threshold of hearing of a frequency of sound. For example, 200 hertz frequency of sound is audible for human ear at an intensity of 10 to the power of negative 10. At a frequency of the sound can be audible a sound with a frequency of 100 hertz is audible at an intensity which is closer to 10 to the power of 8, almost 10 to the power of 7, you can say, pardon, 9, you can say that. Or a frequency of 500 hertz is audible, can be audible at an intensity of 10 to the power of negative 12. As you see, every different frequency will have a different minimum intensity to be audible. So, but generally, human our daily talk is about 1 kilohertz, 1000 hertz. This is the area along which we talked in daily life. That's why in daily life, when you are talking to somebody or if somebody talks to you, their sound intensity, softest sound, the lowest intense sound can be 10 to the power of negative 12. So this is the softest sound you can hear in a daily life about this intensity, which is 1000 hertz. But in this area, very low intense sound can be audible. But when the frequency is small, when we make the frequency small, 50 hertz, 40 hertz, 20 hertz, so you should make the intensity greater. So some sounds can be audible at a very high intensities. These sounds are needs very high intensity to be audible. That sounds also needs a very high intensity to be audible. As you see, 20 kilohertz needs a very big intensity to be audible. 10 kilohertz also needs a big intensity to be audible. But with about 1000 hertz, we hear we need a lowest intensity. So softest sound, this is the lowest intensity of sound which can be audible. Some sounds can be audible at very low intensities. This is the region as you see, but some sounds can be audible at very high intensities. And the softest sound that can be heard by an average human ear occurs at an intensity of 10 to the power of negative 12, about 1000 hertz. As you see at 1000 hertz, the softest sound which we can hear is 10 to the power of negative 12 watt per meter square. This is known as threshold of hearing. Threshold of hearing, 10 to the power of negative 12 watt per meter square. But the loudest sound that human ear can tolerate have an intensity of 1 watt per meter square. This is intensity known as threshold of pain. So this red curve or red line represents the loudest sound. So which is the human ear is can tolerate this sound, but more than that is very dangerous. The highest curve, red curve, represents the threshold of pain at each frequency. So they're almost close each other, 1 watt per meter square. Almost this line is a straight horizontal line. For that, and we can say that for every sound, threshold of pain is almost the same, which is 1 watt per meter squared. And sounds at low frequencies and high frequencies must be relatively intense to be heard. As you see, 20 and 50 hertz sound needs high intensity to be heard, as you see. But also highest sound, 20 kilohertz, needs a very high intensity to be heard. But however, sound in the middle of the spectrum, in the middle, this is the one end, other end, but the middle, needs are audible at lower intensities. As you see, they are audible about 10 to the power of negative 12 watt per meter squared. And exposure to sounds above threshold of pain can cause immediate damage to the ear, even if no pain is felt. So prolonged in a longer time exposure to sound of lower intensity can also damage the ear. So for this reason, many rock musicians wear earplugs during their performance, because high intense sound is really dangerous. So even you shouldn't listen to musics with high intensity in your by headphones. So you should be careful. It can be dangerous. You can damage your ear. And
Teacher,
yes, please.
in this topic, how questions will be asked, teacher,
I,
in this?
I asked so many questions in test bank about them. Why don't you check them? For example, here they can ask. I make quizzes also. I did the quizzes about them. Okay. For example, this could be a question like what? Sounds are audible at sounds at low frequency and high frequencies must be blah 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 to be heard. Must be relatively intense, relatively soft. So no change, for example, such questions.
Oh, okay.
Or they can give this table. Till now they didn't, but they start giving the diagrams, and they start asking questions according to diagram. For example, they can give you a diagram and can say, for example, at 100 hertz or 200 hertz, for example, audibility starts at 10 to the power of negative 10 watt per meter squared. If less than this number, so you cannot hear a sound which is 200 kilohertz. They can give that. A sound is produced at 200 hertz. Which of the following intensity is audible? So 10 to the power of negative 12, 10 to the power of negative 11, 10 to the power of negative 8, none of them. 10 to the power of negative 8 is audible because it is inside this curve. When it is inside, look at here, so 10, 200, so audibility starts at 10 to the power of negative 12, but any intensity greater than this makes 200 hertz sound audible. So such questions can be asked about. And then check the quizzes. I wrote many questions even in the test bank about this titles, these sections. Many questions are asked. Okay?
Okay, teacher. Okay.
And then we will continue with relative intensity. Relative intensity is a little different to the wave intensity or sound intensity, because sound intensity is a subjective calculation. You calculate sound intensity at a point by power divided by 4 pi r squared. You have a very clear, very specific equation, and this equation can tell you what is sound intensity at a specific location from the source. But relative intensity is about human ear, how this sound affects your ear. So relative intensity is talking about that. So wave intensity determines the perceived loudness. This perceived loudness, also known as relative intensity. Of course, this relative intensity depends on how wave intensity is, how big wave intensity is, which means, I mean, if you listen a powerful speaker, you are going to hear a big loudness, or you are going to your ear will hear a intense sound. If less power, I mean low power speaker, if you listen, it's going to be lower. But they are not proportional. Yani which when you make a sound twice as powerful as other one, look at this two, so that sound A and sound B, one of them has a power of 10 watt, say that this is 10, but this is 20, say 20. So of course intensity of this one must be greater than that one, twice of the intensity. So sound A is twice as intense as sound B. Assume it's like this. But you are not going to hear this loudspeaker twice as loud as B. So because human ear is a little spatial created. I mean, it is not getting this sound proportionally loud as the intensity. So unless you are going to see difference between these two sounds will not be, or you are not going to detect difference between these two sounds twice as loud as. So reason for that is this, yani relative intensity does not increase twice. Loudness or relative intensity is not proportional to sound intensity. Yani if I doubles, it doesn't mean that this relative intensity or loudness doubles. It does not. Because God created human ear sensation of the loudness in a different way. In sensation of the loudness in human ear is not directly proportional to the intensity. Logarithmic, it's changing. Yani if it doubles by 2, logarithm 2 is what? Just we are going to change that. If sound intensity doubles by 2, I doubles by 2, logarithm 2 is not, logarithm 2, if I check it, which is equal to 0.3, which means uh, loudness increases by a factor of 0.3. It is not increasing twice. So thanks God. Otherwise, it will be really unbearable world because every sound can make you disturbed, very strongly disturbed. For that reason, it's a maybe perfect creation. Relation between the sound intensity and the loudness and relative intensity is not directly proportional. It's logarithmic, and that's why we are going to get an equation with logarithmic function. Like every measuring scale, relative intensity is also defined according to a standard. So softest sound is chosen as the standard of relative intensity. What is the softest sound? So it is the intensity of that softest sound was 10 to the power of negative 12 watt per meter square. And physicists assume that relative intensity of the softest sound is 0 decibel. So we start hearing at this intensity, relative intensity, when it is 0. And its, of course, corresponding sound intensity will be 10 to the power of negative 12 watt per meter square. And well, because this is the standard, so according to this, we are going to compare other sounds. Relative intensity or decibel level, whose symbol is beta, is defined the ratio of intensity of a given sound to the intensity at threshold of hearing. So we are going to define a given sound. It can be now outside there is thunderstorm, for example. What is the decibel level of thunderstorm? So you are going to write intensity of thunderstorm here. Here you are going to write that threshold of hearing, intensity of threshold of hearing, here IO. And after that, you will divide these two, get the logarithm, multiply by 10, you are going to get the relative intensity of that thunderstorm in your ear. So, as I said, relative intensity is also uh, a dimensionless unit because sound intensity divided by sound intensity, they will simplify each other. That's why it has no dimension, just as the radian in section 1, chapter 1, we talk about that. Unit of relative intensity of decibel level is decibel level, again, decibel level. So because it has no dimension, decibel level is given as the unit for sound relative intensity. And for example, let's calculate what is the relative intensity for a sound at threshold of pain? So remember, at threshold of pain, intensity is 1 watt per meter square. We are going to write here is 1. So 1. Softest sound has a sound intensity 10 to the power negative 12. After that, you are going to get simply the logarithm of this rational number by using your calculator. So but I don't know how, I don't have a calculator right now. I cannot show it to you. 10 to the power negative 12 goes up to the numerator as positive 12. So this 12 in logarithmic operation is taken out of the logarithm, which is 10 times 12, which becomes 120 decibel. So the loudest sound which human ear can tolerate has a sound intensity watt per meter square and a relative intensity 120 decibel. So then sound mustn't be greater than 120 decibel, so it must be less than that. Otherwise, so then you can damage your ear. So the origin of decibel level is bell. Decibel now it's called, but it was initially Bell, named in the honor of Alexander Graham Bell. Surname is Bell, the inventor of the telephone. The decibel is equivalent to 0.1 Bell. Better to know this. Maybe they can ask every small simple questions. So 1 decibel is equal to 0.1 Bell. Better to know this too. And we'll make some calculations. For example, if decibel level is 30 decibel, calculate the sound intensity, corresponding sound intensity at that point. So beta is 30. 30 is equal to 10 logarithm I over IO. IO is 10 to the power negative 12. Simplify by 10, divide by 10, divide by 10, which becomes 3. 3 is equal to logarithm I over IO. I is the question. After that, use logarithmic rule. So like what? Because this logarithm has a base of 10, 10 to the power of 3 is equal to, inside the logarithmic function, the ratio, this ratio, 10 to the power of 3 is equal to the ratio inside the logarithmic function, yani I over IO. Always you do this in logarithm. Cross product, 10 to the power of 3 times 10 to the power negative 12, so which is equal to 10 to the power of negative 9 watt per meter square. So a sound whose decibel level is 30 decibel has an wave intensity which is negative 10 to the power of negative 9 watt per meter squared. And later I showed you a hack for this one. Hack was like this: if you want to get the sound intensity of any sound whose decibel level is given, just write here decibel number, how much is it? 30 is given, right here 30, subtract by 120, divide by 10, you are going to get the exponent of 10. So 30 minus 120, which is equal to negative 90. Negative 90 divided by 10, negative 9. You can use this hack to get the sound intensity of a sound whose decibel level is given. Let's give 60. If it was 60 decibel, you are going to write here is 60. 60 minus 120 is negative 60. Negative 60 divided by 10 is negative 6. So sound intensity of this 60 decibel sound is 10 to the power of negative 6 watt per meter squared. And other questions, when decibel level of a traffic goes in a street from 30 decibel to 60 decibel, how much greater is the intensity of the noise? It's asking the sound intensity increase how many times. So for this one also I used some hack. Didn't I show it here? Oh my God, I forgot to put here. And remember that I was doing like this. This is beta final, 60. Beta initial, which is 30. So ratio of the noise intensities will be, you are going to get the first digit from the left of these numbers and you are going to divide them. 10 to the power of 6 divided by 10 to the power of 3 is your answer. 10 to the power of 6 divided by 10 to the power of 3, which is 10 to the power of 3, yani 1000 times sound noise intensity decreases. Check your malzeme, you are going to see how we solved these questions. They are not so hard. And conceptual challenge question. This is also the same way will be solved. Okay, if you have difficulty today, maybe after the test, we are going to make a live Zoom meeting, so I can solve these questions, problem, solution to you, can show you their solutions. And next title is about the resonance and the forced vibrations. When there are 1, 2, 3, 4 pendulums. All these pendulums are attached to each other by a rubber, you see here, which means when one of them starts to vibrate, other one is going to be forced vibrating. So, but all have different lengths. If their lengths are different, which means their frequencies must be different, because frequency of the vibration of a pendulum is related to their length. Remember, 1 over 2 pi root of G over L was the equation for finding the frequency of the vibration. When a pendulum is set into vibration, for example, you set this pendulum into vibration, it forces other pendulums to vibrate, and other pendulums also will start vibrating because it transfers its vibration to other pendulums. This is called a forced vibration, like this video. So if I show it to you, like it's going to be this way. Yes. Now this is vibrating. So after that, vibration of this pendulum is transferred through this rubber to the other pendulums. This. All they are going to vibrate because this pendulum forces others to vibrate. But sometime later, this three will stop. 1, 2, 3. But this two will continue transferring the vibration. Okay, if their frequencies are equal, yes, because their lengths are equal, their frequencies of vibration are equal. If natural frequencies of the pendulums are not the same, they force each other. The pendulum, which is forced to vibrate, stops vibrating sometime later. These three have different natural frequency than that one. They will stop. They will a little vibrate and stop, a little vibrate and stop. But these two will continuously vibrate. They will transfer the energy from one another. So the force vibration between two pendulums whose lengths are equal, that's why their frequencies are equal, is called resonance. So what happens between these two pendulums is resonance. But what happens between this pendulum and that one, and this pendulum and that one, and this pendulum and that one, is called forced vibration. So then, if the natural frequency of the pendulums are the same, the vibration is completely transferred from one pendulum to another and back again. So this energy transfer between the pendulum repeats several times. And the transfer of vibration or transfer of energy between two systems when their natural frequencies are equal is called resonance. This is another example for the resonance. This is a good animation. Now there are on the left side 3 different lengths of the pendulum, vertical pendulums they are. Another one on the right side, 3 vertical pendulums. So then their lengths, this red and red equal in length, this yellow and yellow equal in length, and the green and green equal in length. So when one of them is set on the right, so the one which is on the left will be the same pendulum, which is the same length, will start vibrating. So let's see it. See that? This and that. Because they're natural frequencies, they transfer energy from one to another one. Red and yellow and yellow, their lengths equal, their natural frequencies are equal. Resonance occurs between these two pendulums. Or green and green. Energy is transferred from this pendulum to that one. So this is an example of resonance. Resonance basically means you can transfer energy from one vibrating system to another if their frequencies are equal. This is called resonance. And resonance in our life, energy is transferred from one system to another, of course, amplitude of the vibration of another system increases. Good example for them, pushing a playground swing. You are going to the playground and then putting your sister or the other elder sister and the other sitting on the swing. So if you want this swing to greater amplitude, you should push the swing and the frequency of the swing and frequency of your hand must be the same, and you can increase the amplitude, you can energy to the swing. By adding the energy to a glass, you can break it because every molecules in the glass are vibrating. So if you produce a sound which has exactly the same frequency of this molecules of the glass, so it's possible to add energy to the glass and you can break the glass. Or diffraction of Tekano-Narrows. It's a kind of resonance too. Bridge is vibrating. This bridge is vibrating, but not visible initially. Then wind is blowing so that it can add energy to the bridge and then cause its vibration to be much stronger. And finally, this bridge is collapsed. All these three examples are based on the resonance. So resonance is a very effective energy transfer method from one system to another. And there is a specific type of forced vibration we have, which is known as sympathetic vibration. It's about the musical device generally. Remember, sound is produced by vibrating objects. So in a guitar, you are vibrating the guitar string, and these strings are making sound. But this string is attached to the body of the guitar by a bridge. This is called bridge. As string is vibrating, these strings are set into vibration. This vibrating string forces this bridge to vibrate. So because they are in contact, these strings are in contact with the bridge. Number of vibration of the frequency of these strings, vibrating strings, forces the bridge to vibrate with the same frequency, and the bridge vibrates the body of the guitar with the same frequency. So the vibrating strings of the guitar forces the bridge of the guitar to vibrate, and bridge transfers this vibration or forces the guitar body to vibrate. So this is called sympathetic vibration. This chain of forced vibrations are called sympathetic vibrations. In fact, they are a kind of forced vibration. String vibrates the bridge vibrates the body. So body transfers the vibration to the air as a sound, as an intense sound. Because guitar body has a larger area than strings, guitar body enables the string vibration to be transferred to the air at a greater rate, more efficiently. That's why intensity of sound increases. If you don't use the body, if you use only the string, intensity cannot be so high. But if you use the guitar, because so many molecules will be in contact with the guitar body, energy from the string, it can easily be transferred to the air and sound intensity can be increased. However, if you use the guitar body, strings vibration dies out faster. I mean, the vibration cannot continue for a longer time because if energy is lost very quickly to the air, so then vibration will stop in a shorter time. This is the sympathetic vibration. As I said, it's a forced vibration starting from the vibrating string to the bridge, then from bridge to the air, from bridge to the guitar body, then from the guitar body to the air. So all these substances are vibrating with the same frequencies because this string forces bridge to vibrate with the same frequency. This bridge forces body to vibrate with the same frequency. Body forces the air molecules to vibrate with the same frequency. So this chain of forced vibration is known as sympathetic vibrations. And this is all about section 2. Any questions about section 2?
No, teacher.
All right. So then section 3, it will not take so long. So let's finish the section 3. And then we will finish today's course. Let me open section 3. Section 3 is about the musical instruments. So then we know that, yes, you can produce a sound by waves, but how? How can you change the frequency of a sound? Or frequency of a sound depends on what? Frequency of an instrument depends on what? We are going to talk about this in this section 3, which is titled is about the harmonics, which is known as harmonics. Okay, let's screen share first. So you can see the screen right now.
Yes.
Okay, so first we should know that harmonics about standing objects, standing waves, sorry. Sound can be produced by standing waves produced on a vibrating strings. So then origin of the sound for every type of instrument is standing waves. So we will start with a string instrument. String standing waves on a string are on a vibrating string generates a sound. As you hit a guitar body, so you make the strings to be vibrated. These strings are starting to vibrate and they form standing waves. The standing waves on this guitar string forms the sound because every standing wave will have a different frequency, and that's why this guitar will be mixture of different frequencies and will make a lovely sound. Standing waves are formed at certain frequencies and wavelengths. We studied it in the section 3 chapter 3, section 4 chapter 3. Frequency of the sound produced by a string is equal to the frequency of the standing waves. Okay, so as we said, the standing waves on a string produces the sound. All right, and when a string is set into vibration, there are several possible vibrations may form on an idealized strings. So we are going to study those possible vibrations. Uh, First, we should know that in a string, when a string is set into vibration, so there forms the standing waves, and the ends of the string, which is not vibrating, because they are fixed, cannot vibrate. These ends cannot vibrate, and they are always note. Yani ends are notes. But the string experiences the most displacement between two notes. Between two notes, the region of the longest displacement, a longer amplitude, is known as antinote, as we learned before. And distance from note to note or antinote to antinote is half of a wavelength, lambda over 2, and we know this before. And possible standing waves on a vibrating string is starting from the lowest frequency and with longest wavelength, which is known as first harmonic or first order standing wave. This is first order standing wave. This is first harmonic. Yeah, this is a string which is vibrating at smallest frequency and longest wavelength. Lowest possible frequency that produces a standing wave is called fundamental frequency. No less frequencies available. No lower frequency can form a standing wave on a string. So this is the smallest frequency. And because frequency is smallest, standing wave gets the longest possible wavelength here. And we can get it by shape. Look at the shape. Length of the string is equal to half of the wavelength. How do we know that? Because from note to next note, separation is half wavelength. So then length of the string is equal to lambda over 2. So lambda is equal to v divided by f. We know from this speed equation. If you cross product it, you get the equation for calculating the fundamental frequency, which is v over 2l. So this f1 fundamental frequency depends on the speed of the wave in this string and of course length of the string. This standing wave is named as the first harmonic, consists of one loop, one antinote, and two notes. But other possible standing waves, of course there are other possible standing waves, second harmonic, third harmonic, fourth, fifth, and so on. Only what? In second harmonic, we have two loops, one, two loops, two antinodes, but three notes. This second harmonic will have a frequency which is twice of the first one. Third harmonic, three loops, three antinodes, four notes. Number of notes will be one greater than number of antinodes. So third harmonic will have a frequency which is three times of the fundamental frequency. Fourth harmonic will have four loops, four antinodes, and five notes. And fourth harmonic will have four times of the fundamental frequency. And all harmonics are present in a string instruments. An equation for harmonic series of standing waves on a vibrating string can be written as n times V over 2L. Remember, V over 2L is the fundamental frequency, and n times fundamental frequency, where n is 1, 2, 3, 4, and so on, and known as order of harmonics or number of loops, also number of antinodes. This n is representing. Two factors determine the frequency of the harmonic series, if you look at this equation. One of them is speed of the wave in the string. So, of course, there are waves which is moving back and forth in a string, which forms standing wave, and the length of the string. So, if you are able to change the speed of the wave in the string and the length, for example, when you are playing the guitar, you can make the speed faster if you stretch the string. You can make the wave move faster. You can change the frequency. Or by pressing your finger, you can change the length. When length changes, also fundamental frequency also changes. Note that V in this equation is not speed of the wave in the it's the speed of wave in the vibrating string. Yes, it is not the speed of sound. Be careful. Sometimes you get confused. Speed of sound in air is not that one. This is the speed of the wave in the string, in moving in the string. If the string vibrates at one of these frequencies, F1, F2, F3, F4 of harmonic series, the sound wave produced in air will have the same frequency of the string, because always wave has the same frequency of the source. Whatever the source frequency is, sound will have the same frequency. And as I said, two factors determine frequency of the harmonic series. One of them is the speed of the wave in the string. Second one is length of the string. I put here is a video. Maybe this video is about it. I forget what it's about. It is sound, so that's why I will skip it. Problems are not sorry about this. We're going to use basic equation, which is V over 2L times n to calculate the frequencies. And second instrument which makes a sound is tubes, open ends and closed end tubes. When disturbance is produced at one end of an air column, it travels through the pipe as longitudinal wave. So you are blowing one end of this air column and then making disturbance. This disturbance is starting to move back and forth along this pipe, which forms the standing waves. If both ends of the pipe are open, so open end pipe, all harmonics are present. So which is N1, N2, N3, N4, all harmonics can be formed. When longitudinal waves are produced from one end, you are blowing one end of the pipe. So longitudinal waves are traveling down to the pipe, but from this free end reflects back. When they reflect back and you continuously blowing, so this going down waves and reflected waves interfere with each other and then form standing wave. So when longitudinal waves arrive open end here, they reflect back and interfere with other waves which is traveling down and produces standing waves. And this standing waves produces the sound. Air molecules at open end have complete freedom of vibration. For that is an open end treats as an antinode. Open ends are antinodes. So antinode exists at both ends. And between two antinodes, of course, there must be a note. Here in both and open pipe, number of antinodes are greater than number of notes. It's opposite of string. In string, number of notes one greater than antinodes, but here number of antinodes are one greater than number of notes. One note exists between two antinodes. Number of notes is always one less than the number of antinodes in an open end, or both ends open pipe. And equations are the same. I will not continue this part, just equation. The equation for harmonic series of the pipe open at both ends is the same as the equation of the harmonics at a string fixed at two ends. So which is Fn is equal to N, V divided by 2L. N is again 1, 2, 3, 4, 5, and all harmonics are present for pipe open at both ends. And two factors again determines the frequency of the harmonic series. One of them is again speed of the wave inside the pipe, which is air normally. Inside there is the air. And of course, length of the pipe. So you can change the length of the pipe. There are some openings. You can press your finger, close these openings and open these openings, and then which are called keys. And you can make the pipe longer and shorter, and then you can change the frequency of the sound produced by this device. Flute is a similar example to a pipe open at both ends. So you blow the flute, but just blowing point, there's an open end above, and below the bottom is also, the other end is also open. So that's why flute is a device which is open at both ends. As I said, two factors determine the frequencies of the harmonic series. Here are some videos about that: speed of the wave in the air column and length of the air column. Speed of the wave, you can change speed of the wave by changing the medium. Remember the people who are breathing the helium. So helium is light gas. That's why speed of the wave in the helium is faster. That's why you are going to hear a higher pitch. Funny voice is coming from this, but also it's possible to use other heavy gases like sulfur hexafluoride. So this wave is moving slower, and when it's moving slower, frequency decreases, pitch drops. You hear a funny voice, but this is the reverse of the helium. It's like Donald Duck voice. Length of the air column is also possible. You can press the holes and then close the holes and open the holes. You can change the length of the instrument, and then you choose sound. And last, the voice pipes close at one end. So one end is closed. In the of instrument, only all harmonics are present. 1, 3, 5, 7, 2, 4, 6. They don't exist. So air molecules closed and are restricted to vibrate. So notes exist at closed end. Open ends are antinodes, but closed end are notes. So for that, as in a closed end pipe, one closed pipe, no antinodes are equal. One no antinodes, one note. Two antinodes, two notes. Three antinodes, three notes. Equation for harmonic series for pipe closed at one end is slightly different. Fn is equal to N divided by not 2L, 4L. And don't forget, N is equal to 1, 3, 5, 7. Yani only odd harmonics are present in a closed end pipe. And trumpet, saxophones, and clarinets are similar to pipes closed at one end. And the last title of this section is about the sound quality and timbre. As I said, a variety of standing waves can occur when a string is set into vibration or a column is blown. Sound waves from an instrument consist actually multiple frequencies, which means multiple harmonics. When you play a guitar, or when you play a violin, or when you play an instrument, the clarinet or saxophone, more than one harmonics exists at the same time. And mixture of these harmonics produces the characteristic sound of that instrument, which is called as sound quality or timbre. For example, tuning fork is the simplest musical instrument. It's the simplest device which makes the sound. But tuning fork only vibrates at one frequency, fundamental frequency. No other harmonics exist. That's why tuning fork, because vibrating with simple harmonic motion, the waveform of tuning fork is also simple harmonic. It's a sine wave, resultant waveform. So tuning fork vibrate only at fundamental frequency, as you see, n is equal to 1. And its waveform is very sine wave. It's very, the repeating, not so complex. But other instruments are not like this. Clarinet, for example. Clarinet has multiple harmonics. First, third are very dominant. Odd harmonics are very dominant. So even harmonics are not so dominant here. Yeah, second exists, but not dominant. So mixture of all these harmonics is making the sound of clarinet. So other instruments vibrate at different frequencies, at different intensities. Yes, first fun, second harmonic, third harmonic. First harmonic is, yeah, some intense, but third harmonic is more intense than the first. And the second harmonic is less intense than first and third. And then fifth is much more less intense than this one. Okay, as you see, intensity of the harmonic is different. Each harmonic is a sine wave. Yes, each harmonic is a sine wave, like first harmonic, like second harmonic, like third harmonic. But combination of these harmonics is making a wave pattern which is complex, not simple. So resultant wave pattern of clarinet is not so simple as a tuning fork. It is a little complex, resultant waveform, but it's repeating waveform. So then as you see, from here to there, from here to there, from here to there, it is repeating. This repeating wave pattern is called periodic. The waveform of every instrument consists of repeating patterns. Such waveforms are said to be periodic. If something repeats itself, it's called periodic in maths, in science. And in musical instruments, mostly fundamental frequency determines the pitch. And there are other harmonics also available, second harmonic, third harmonic, fourth, and so on. Those harmonics are called overtones. For example, second harmonic is called first overtone, second overtone, fourth is going to be called third overtone, and overtones. And in scale, there are 12 notes. 12 notes. The frequency of the 13th note is exactly twice that of the first note. So look at here, first note has a frequency of 440 hertz. Second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10, 11, 12. After coming 13, 13th note has a frequency of 880, which is twice of the first note. And together, all together, this 13th note, this H, this interval, in and okay, this range of notes from first note till 13 altogether forms an octave in musical literature. And reverberation is the last title, which is the means repetitive echo sound from the ceilings, walls, floors, and other surfaces, called reverberation. So in mosques, for example, reverberation is very powerful, but auditoriums are designed to minimize reverberation. For that reason, maybe you will see that auditoriums have textured materials and then not so flat. All these are have some purpose to make like this. So for speech to be clear, the reverberation time, what is reverberation time? The amount of time, you are going to count the seconds, it takes for sound intensity to decrease by 60 decibel. We want sound intensity to decrease as it is reflecting. Otherwise, reflection and continuous speaking will mix each other, and then you cannot clearly understand what person is talking or what music is played. For speech to be clearly heard, this reverberation time in auditorium must be very short. So then reflection, because of the reflection, so it must stop quickly. Ceilings in the library and other quiet places are often made soft and textured material to muffle, to absorb the sound. Look at this is the radio studio. As you see, walls are textured because we don't want reflection, because if sound is reflected, so original sound and the reflected sound, so the sounds mix each other so that you cannot hear the somebody which is clearer.